In this video, we are going to analyze the Thomas-Fermi model, which is actually a kind of first density functional theory. It was derived by Thomas and Fermi independently in 1927, and the main aim they had was to describe the electronic density in an atom. This is a quite challenging problem. Nowadays as well, it's a challenging problem because have in mind that around a nucleus we do have like a charge density, and this is the electrons, many electrons, and they are interacting very strongly each other, and solving the Schrodinger equation for that and getting the wave function, the total wave function for corresponding to the whole electronic system, it's a very tough problem nowadays as well. So they thought, okay, if it may be interesting, instead of solving the Schrodinger equation and getting the wave function, getting the electronic density corresponding to the atom. So for that, of course, we need the equation that the electronic density satisfies. So they refused to get the wave functions, and maybe, yes, characterizing the electronic density, we might be able to characterize the electronic properties of the atom. The atom was the main objective they had, even though actually they could apply that model to any other system as well. And the starting point for that was getting an expression for the total energy of the system as a function, therefore a functional of the electronic density. And of course, the total energy has a kinetic energy contribution and the total potential energy contribution. And actually, the toughest part was having the functional for the kinetic energy. We don't have a functional for the kinetic energy. Of course, we do know which is the expression for the total kinetic energy in terms of the wave function, but we don't have the functional of the kinetic energy in terms of the electronic density. And for that, in order to have the contribution associated to the kinetic energy, they considered an approximation. And the approximation they took was the kinetic energy for the uniform electron gas. So if you remember, the kinetic energy per particle, or the expression for the kinetic energy per particle in the uniform gas was that 3/10, 3 pi square over 2/3 times the electronic density, 2/3. And this is the total kinetic energy per particle. If you multiply that times the number of particles we do have per unit volume, you do have the kinetic energy per unit volume. So you do have like the kinetic energy density. So if you multiply that, basically means that you have n, the kinetic energy, to the power of 5/3. Okay, but actually here in the uniform gas approximation, the electronic density is a constant. But in the atom, the electronic density is not constant. It varies with the position vector. So they considered that, okay, even though this expression is exact for when the electronic density is constant, we'll consider that the variations on the density in an atom are slow enough so that we could apply that, but considering that the density is going to be spatial dependent. So they consider that approximation, but plugging here the spatial dependence on the electronic density for the kinetic energy density. And if we want to have the total kinetic energy, what we have to do is to integrate on the whole space here. And this is the expression we do have here. So therefore, here, that's the expression of the functional, in this case, of the kinetic energy in terms of the electronic density, considering the free electron gas approximation, but including the spatial dependence of the electronic density. And actually, to make the expressions more to look nicer, this coefficient here, it's going to appear later as well, because that expression is the one that we're going to use. We're going to call it AK, okay, for later. So that's the kinetic energy, and the rest actually is the potential energy. It's the total potential energy. And the total potential energy has two contributions here, this and this one. The first contribution here is the electrostatic potential energy, the interaction potential energy, corresponding to electronic density and R. If you have electronic density and R, the interaction potential energy corresponding to that one is given by this expression here. It's actually a classical expression for the interaction potential energy whenever we have that electronic density. And besides that, you also have an external potential, because the external potential in this case, for the atomic case, will be the potential which is associated by this external charge, which is the nuclear here. And this, the electronic charge density is going to fill the external potential induced by this nuclear here. So we do have, this is the external potential energy. And the sum of the two are the total potential energy. As you can see here, this is just a classical approximation for classical expression for the electrostatic potential. So you are combining somehow, this is a classical result with another result here, which is somehow a quantum result here, because in order to have that, we're considering that the electrons are have plane waves, that they are obeying the Pauli exclusion principle, so the two electrons cannot be in the same state, so they are filling different state and reaching the Fermi state, and so on and so forth. So this is like a quantum result. So you are combining these quantum results and classical results. That's why this Thomas-Fermi approximation is usually called a semi-classical approximation here. So the starting point again is going to be that energy functional, and next what we are going to do is, in order to have the equation that this electronic density is going to satisfy, considering that energy function we do have, we are going to minimize that energy function with respect to electronic density. And that's what we are going to do next. So here, the equation that this electronic density is going to satisfy is the one coming from the minimization of the electronic density, but considering the constraint that the total number of electrons is going to be fixed. So that equation has to be satisfied. So, and we do know how to do that. For that minimization with a constraint, we apply the Lagrange multiplier method. So in order to do that, we define a new functional, which is going to be f, which is just basically e, the previously defined one, minus mu, that's going to be the Lagrange multiplier, and this is times the constraint we have to consider here. And now what we are going to do in order to get the equation of the electronic densities, so we minimize this functional f with respect to the density. And actually, when we are doing that, we can actually find a physical interpretation for this Lagrange multiplier mu here, because the functional derivative of f with respect to n, as f has basically two terms here, basically is the functional derivative of E, the energy, with respect to n, minus mu times this functional derivative of this term here with respect to n, which basically is 1. So that has to be 0. Or if we write in this way and we pass this mu to the other side, what we do have is that mu is basically the functional derivative of the energy with respect to the electronic density. And that's basically the definition of the chemical potential. It's basically saying you how much the energy changes with respect to the change of the electronic density. Okay, we do have therefore the physical interpretation of mu, which is going to be a constant here. So doing therefore the functional derivative of f with respect to n, that's very straightforward. Just consider the expression we do have before, the function we do have before, of the total energy in terms of the electronic density, and doing the functional derivative of this term in terms of the density. It's very simple actually, and this is the result we do have. And then minus mu times 1, and then mu passes to the other side like that, so that's going to be equal to mu. So this is actually the Thomas-Fermi equations that we do have for the electronic density here in the integral form. As you can see here, you have that this electronic density is inside an integral. So these are therefore the Thomas-Fermi equations. And again here, that equation, that term here, it's actually called the induced potential associated to this electronic charge. We are going to call it V. That's going to be the induced potential. So that's one of the ways we do have to express these Thomas-Fermi equations. But there is, in order to make them more tractable and easier to solve, we're going to write them in a different way. We're going to write them in a differential form and not in the integral form. So, and for that, we are going to play with that induced potential here. So how we are going to do that, that's going to come next. So here we're going to see how the Thomas-Fermi equations look in the differential form here. So for that, again, remember that this is the induced potential we have just defined, and the Poisson equation for that induced potential basically is this one. So as you can see here, the Laplacian of the induced potential is basically proportional to the electronic density. And in the equations before, here, you can extract basically you can write the electronic density in terms of the external potential and induced potential. So if you isolate here from here the electronic density and write it in terms of the external potential and the induced potential, the result what you have is this one. So this is the electronic density in terms of the external potential, induced potential, and mu. Okay, and remember that the electronic density is basically proportional to the Laplacian of the induced potential, so that you can replace that electronic density with this one, with the Laplacian of the induced potential times a constant. So, and if you are doing that, the final equation you do have for the Thomas-Fermi equations, but now in the differential form for the induced potential, is given by this expression here. So we do have a differential equation for B. And of course, if you are solving that equation, after solving that equation, if you have the V, the expression for B, then just making the Laplacian of V, you are getting the induced the electronic density. So getting the induced potential is equivalent to get the electronic density just using the Poisson equation here. So just summarizing, we have finally got the differential form for Thomas-Fermi equation for the induced potential, which is equivalent to get to the electronic density, which is in terms here we do have the chemical potential, which is going to be constant, and the external potential. So first, of course, we have to, in order to specify it as equation, you need to specify the system we do have, which actually is equivalent to specify the external potential, which actually depends on the system. Of course, if you do have an atom, that atom is going to be determine what's going to be the external potential we do have. And for each particular system, we have to determine what is the chemical potential, which is going to be a constant. So once you have that external potential corresponding to the system you want to analyze, once you have the chemical potential corresponding to the system which you have to analyze, then you are finally need to solve that equation in order to get, again, the induced potential and the electronic density. And in the next, what we are going to do, we are going to apply that Thomas-Fermi model here for an atom in order to get the electronic distribution corresponding to an atom.